Hi everyone, this is going to be a short pre-lab lecture on how to complete the molecular modeling worksheet for our very last lab. So why don't we get started? It's only a couple of slides. I'll do an example with you for one of them, and then I'm going to show you an interesting website that helps visualize what the molecules look like in three-dimensional space. Now that we don't really have the ability to play with the modeling kits themselves, a lot of it's going to have to be done in your own imagination. But also that website, and I'll send that along later, will help as well. So a lot of this is just going to be going over like a reminder of things that you've done in lecture. And the first thing we're going to need to get under our belt before we even start drawing what a molecule looks like is to determine the amount of electron domains around a center atom. And so what I mean by a center atom is exactly what it sounds like. We're keeping, for the majority of our models that we'll be drawing today, I think except for maybe a handful, maybe like 2 or 3, there won't be a center, there will be a center atom. Sometimes you might get something, if we saw something like ethene, I just drew on the screen, there really isn't a center atom. So if you do come across something like this in the worksheet, what you do is you ask yourself the question, if I sat on carbon number 1, what is my electron geometry? If I sit on carbon number 2, I ask myself, what is the electron domain geometry? I'll give you the heads up too that everything has been designed for this worksheet, that if you do have something like this example where there's no center atom per se, that both of those atoms that are near the center will have the same electron domain geometry. So that should be a little bit of a help. So what do I mean by electron domains, right? The way I've always kind of phrased it are just things around the center atom. And I'll explain what I mean in a second as soon as I'm done writing. So things around the center atom. And that's why I put things in quotes, is because it can either be a bond or it could be a lone pair. Both we're going to count as things. And then I'll show you in an example what I mean by things, right? But if we can count up the number of places around an atom where there's electron density, that will give us the total amount of electron domains. So you should already have a handout, I believe, for summarizing what is the geometry going to look like based on the amount of electron domains around that center atom. So if we have a center atom and there's only 2 electron domains, right? The electron clouds, they're negatively charged, so they actually will repulse each other. And so the way that it alleviates that amount of that stress that's there is to keep the electron domains as far apart as possible. And so the furthest you can get away from something is a straight line. And so that's why we see a linear geometry. So an example of a linear molecule would be something, say, like this, when we have carbon disulfide, where we have our center carbon and it's surrounded by 2 other atoms. So even though it looks like there's 4 bonds, what we want to do when we're counting domains is just the whole thing. So that would be considered 1 electron domain around the center carbon, and then all of this would be considered the 2nd electron domain around that center atom. So it's not necessarily the number of bonds. We want to think of them as like areas of concentrated electron density, and that's what we're counting up. So that would be an example of a linear molecule. The next one would be if we had 3 electron domains and we'd get a trigonal planar geometry. Again, we're having these pockets or these areas of high electron density. The negative charge repulses. So if there's 3 things around a center atom that are trying to get away from each other, the furthest you can be from the neighboring atom or the neighboring electron domain is going to be on an equilateral triangle at 120 degrees apart. So something like this might be borohydride, where we have a boron in the center, and then we have 3 electron domains around that center atom. And again, when we're counting domains, 1, 2, 3. right? We said it doesn't matter if it's a bond or a lone pair. So we'd have an electron domain of trigonal planar. I'm not going to go through all of them, but this is how we start to build things up, right? And so the last one I'll do is tetrahedral, and we'll leave it at that. There's just two things I want to point out. So if we took the example of, say, water, and then let's do something like methane, right? So if I drew out the Lewis dot structure for water, it would look something like this, where I have 2 hydrogen and then 2 lone pair. When I'm counting up the number of electron domains, 1, 2, 3, 4. That's going to give me a tetrahedral shape. And again, they're trying to stay away from each other as far as you can. So it makes a tetrahedral shape, so kind of like a pyramid, where all of the electron domains point away from each other at about 109.5 degrees. If I did the same thing with methane, the CH4, right? I would show something roughly like this, right? So I have that center carbon, and then I have 4 hydrogens attached to it, again in a tetrahedral electron domain geometry. One thing that I want to point out that we're going to start to practice drawing, and then if this throws you off, you're more than welcome to find help online. That's fine with me. It's mostly getting practice in drawing. What we're going to focus on is trying to give perspective. And what you're trying to do is approximate, that's not a good approximation, approximate the 3D structure. And so what I've shown here is doing my best to try and approximate. Actually, let me see if I can make that a little bit better. If I switch something like this, there we go, right? I'm trying to approximate that shape of the tetrahedron. And the way that chemists do this is we use 3 different types of bonds per se. One is the normal, just a line that you see here for those 2 top hydrogens. That's telling me that those bonds are in plane with the screen. And so basically it's like a flat molecule, that H, the C, and H. If I'm implying that something is coming toward me, basically we're trying to use like a vanishing point type thing. It's like looking like there's a bold line coming towards you. So we use a filled in triangle to insinuate that this hydrogen's coming actually out of the screen or out of the board at you to try to give you perspective. And then the last one would be this hash mark you see to the left. That's telling me that that H is going back into the screen. So trying to give you that perspective that it's going away from you. So we use the hash marks to say it's kind of fading into the distance. So it does take some practice to get good at drawing these, but part of the grade for this is doing your best to show correct geometry roughly and show roughly correct orientation in space. So here are just some examples. You can go through that. Just one thing I do want to point out. I know we've gone through this in lecture. It wasn't on the last slide. On the last slide, we were looking at electron domain geometry and electron domains, the number. The last thing I want to talk about is going to be molecular geometry. And in this case, electron domain geometry, we didn't make a distinction between lone pairs or bonds. Molecular geometry only looks at bonds. You don't include the electron domains. So what I want to show then as an example is down here for ammonia, right? A good example here is if we count up the number of electron domains. I got 1, 2, 3, and 4. So there's 4 electron domains, but there's actually only 3 atoms. And so I think you guys have gone over this in lecture before, so you should have a handout that helps you work your way through these, right? So when we have an electron domain, well, it's definitely tetrahedral. There's 4 areas of electron density. However, if we're just looking at the shape of the atoms, it's actually going to be trigonal pyramidal. And if I was going to, let me see if I can find some space to draw that correctly, right? We put our lone pair in on the nitrogen. And if I was going to do this more correctly than the sketch that I have over here, would be to use my hash marks and my filled in triangles to try to give some kind of 3D spatial representation for ammonia. And so that's what we see here. So if we imagine we don't have the lone pair on there, we can't see four things. But if we look at the rough shape of it, it kind of looks like a pyramid and has a triangle base. So we're going to call that trigonal pyramidal, despite actually having a tetrahedral electron domain geometry. So it's a subtle difference between the two, and it's going to come with practice. One of the other things I'm going to have you do once you've drawn your structures is to start determining what type of bonds are being formed, right? And so we deal with two types of bonds in Gen Chem 1. Those are going to be sigma bonds and pi bonds, right? So just going a little bit into the theory a little bit. We won't go too deep because I know you did this in lecture and it's not absolutely necessary to complete this worksheet, but it's definitely good to understand. It's how these bonds are formed, right? The reason why they're called sigma bonds is because sigma is the Greek S, and it starts with either a combination of two S atomic orbitals or a combination of an S and a P atomic orbital. When they overlap, they hybridize, and you actually make new orbitals. The easiest way to figure out if something is a sigma bond is if you draw a structure. Let's do something like this. I'll put a double bond in there. So we got 1, 2, throw an H over there. I'm just making this molecule up on the spot. Right? If I had to go through this molecule and then label how many sigma bonds I have, the easiest way to do it is to just draw the structure as if it were just a skeleton. And so you can see I deleted that double bond because the skeleton, the minimum amount of connectivity is 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds in that structure. Anything that is more than a sigma bond, so like a double bond, we are now, let me put that into a different color, I'll make it red, right? The original structure had that double bond. Well, that one I drew in red is actually a pi bond, and it comes from the overlap of two p atomic orbitals, and they form a single bond. So it looks a little bit confusing, but take-home message is if you can count up the skeleton, those are all sigma bonds, and then any additional bond, like a double or a triple, will each count as one pi bond. So let me just use one more example. Let's say we have this molecule here. Let me make this more explicit. That should be enough bonds for everything, right? If we did this again, right, we look for our skeleton, 1, 2, 3, 4, 5, 6, 7, so 7 sigma. And then I take a look at how many pi bonds I have, 1, 2 more pi bonds. So 7 sigma and then 2 pi bonds. One of the questions is also going to ask you to draw an isomer. So an isomer, if we break down the Greek, it means same pieces, or roughly translate to same pieces. So what you see down here is both of these molecules have the same molecular formula of C2H4Cl2, but they can be connected differently in space, right? So if I take a look at this first molecule, I can see the chlorines are attached to 2 different carbons, right? I must make sure I've used up all of my atoms. I got 2 chlorines, I got 1, 2, 3, 4 hydrogen, and then 2 carbon, so I'm in good shape. If I compare that to the second structure, go through, I got 2 carbons, I got 4 hydrogens, yep, and then 2 chlorine, I'm in good shape. But take a look where the chlorines are now. The chlorines are on the same carbon. We don't know how to name compounds yet, but so I won't give you the whole name, but the way we would kind of keep track of where our chlorine is in number 1 is 1,2-dichloro. And then you'd add the end of the name on. We don't know how to do that. I'm just trying to make a point here. And then this second structure would be called 1,1-dichloro. And then you'd put in the rest of the name after that. So if it has a different name, it is a different structure. The one thing I do want to point out, and you don't have to name them, but this is what happens a lot with students. So I'm going to take this example A lot of times students will try to write another isomer and they'll draw something that looks like this, where it looks different on paper because on the first structure, both chlorines are on different carbons, but they're pointing up. Then in my structure over here, I have chlorines on different carbons, but the chlorines are pointed down. They're actually the same molecule, because look what happens if I kind of rotate it in space. Remember, molecules exist in 3D space. This molecule would look exactly like this. They're exactly the same, so they're actually not isomers. They'd be the same molecule. So make sure you're keeping track of that in your head. Sometimes you have to kind of manipulate things in space to see if, in your mind, is it the same molecule that I drew, or is it something different? So the directions for the worksheet, technically this is due at the end of class. I'll allow you guys to turn it in a week late, not a week late, but like the regular due date. We try to usually get things done today. If you get things done today, you're good, you're done. But I'll allow you to turn it in up to next Thursday at 9 a.m. or 9:25 a.m. So the directions are, you need to work directly on the worksheet. If you can use loose leaf paper, that's fine. It does need to be neat. If I can't read what you're doing, then you're going to lose points on that. So it does need to be neat. We usually would have modeling kits in the lab with us. So I'll usually be building a model of each molecule to help you visualize this. What I'm going to do instead is Professor Lando and myself, we found a pretty good website that it's only a select few. It's not going to be like all of these examples, but you can actually see in space what it would look like. And so I will send you the link to that. And before I stop the lecture, I'm also going to show you what the link looks like, right? Your 3D sketches should contain lone pairs only on the center atom. So you don't need to, if you have other atoms around that center atom, you don't need to show all the lone pairs. So if you had something, let me draw it real quick. I only draw a piece of a molecule. But if you had something like a carbon connected to a chlorine, right, usually you could draw in all the dot structures on the chlorine. I'm fine if you don't. You can just leave it as, that center carbon, and then it has the chlorine attached. Even though the chlorine, if you drew it the dot structure, it would have had 7 electrons. So I've crossed out some other stuff. Like obviously you can't show me a model, so we're not going to be doing that. Make sure you include bond angles. If there's more than one, don't go overboard. Like it doesn't have to be every single angle. Just, if you have 2 different angles, like maybe one is 90 and the other one's 180, just label one of each type. It doesn't have to be the whole molecule. For types of bonds, this goes back to that last slide I was showing you. I need you to say, is it single, is it double, or it's triple? And then also say how many sigma and how many pi bonds there are. Right, just like I was doing before. Is there 7 sigma and 2 pi, something like that. And then the very last molecule, you're going to be asked to draw 3 isomers. So make sure you double check. You're going to have to do that in your head. Ask yourself the question, is this the same molecule? Have I just drawn it differently on paper? Because nature doesn't care what you drew on paper. It's going to care what the molecule actually behaves like. So make sure you put some thought into that. So that ends this section of the pre-lab lecture, where it's just the slides. So what I'm going to do is I'm going to change, share this other, there we go. So I'll send out this link as well, but it's really useful because you actually can see how the molecule actually responds if you start moving things around. Here I have water. You can see the lone pairs are there. You can see how the hydrogen is bent. So you have a bunch of options. It can help you, figure out what the bond angle is. It gives you the molecular geometry and the electron domain geometry, right? There's only a handful of molecules, some of them which you do have on your worksheet, others you don't. But I think it's a real good way to, at least, especially if you're getting stuck and having a hard time visualizing, coming to this site might actually be really beneficial. All right, with that, I'm going to stop pre-lab lecture. I'll be on Zoom from 11 to 12 this afternoon if there's anyone needs any help. But like I said, I'll be here from 11 to noon on Zoom. It will be, try to get it done today. It's not that bad. You spend 3 hours, you get it done, and then you're done for the rest of the semester in terms of work for lab. But like I said, if things are busy and things are hectic and you can't get it done today, it will be due at 9:25 a.m. next Thursday. All right, hope everyone's still doing pretty well out there, holding it together. I'll talk to you all later.